Hi everyone. In this review, I will be going over LSD sort, I will be going over counting sort, and then we'll be doing an understanding problem, which I think is rather clever and fun. Okay, but a quick disclaimer, we won't be going over MSD sort. If you want a review on that, watch problem 2 in this exam prep recording playlist. All right, so when we approach radix sorts, the problem that radix sorts help us solve is, what if the items we are sorting are composed of digits? Could it be faster to sort all of these items going digit by digit instead of, I don't know, using quicksort or merge sort or any other sorting algorithm we've learned so far? Okay, so the first way we've learned of approaching this, I don't know, radix sort idea is called LSD radix sort. So what's happening here is we're going to repeatedly sort the same list of numbers, and we're going to assume they're numbers for this walkthrough, but they could be anything that are composed of like digits, like strings. So we're going to repeatedly sort the same list on each digit, okay? And we're going to be going from the least significant digit to the most significant digit, okay? So as a quick example, suppose we have this list of numbers and we want them sorted, right? So what we're going to do is we're first going to sort all of these numbers on this last digit. And this last digit is called the least significant digit in a number, okay? And what's very important here is that when we sort all of these numbers on this last digit, we're going to do so in a stable fashion, okay? This may not seem like too needed right now, but we'll soon realize that it's very important that it's stable, okay? So what we'll notice is that the two numbers whose last digit are 0 are ordered the same in this sorted ordering, okay? Then what we're going to do is sort all of these numbers on the second to last digit. Finally, we're going to sort all of these numbers on the most significant digit or the first digit, and we'll see that magically these are now in sorted order. Okay, so I still haven't gotten around to the fact of how exactly are we going to sort all of these numbers on this digit, right? Well, we actually could use any stable sorting algorithm, right? But we'll soon see that counting sort tends to work really, really well here as the way for us to sort all of these numbers on a particular digit, okay? But let's first take a step back and ask ourselves, why does LSD sort really work, right? It seems like a little too magical to work for me, at least. So when we approach a sorting algorithm and we're trying to convince ourselves that it works, let's, I don't know, see how we can do so. So suppose we have two numbers, A and B. Okay, so if A is less than B, does LSD radix sort ensure that A comes before B in the final sorted array? So all I've done here is I've asked a more specific question, right? And instead of asking, why does this work? Now we're asking, in order for a sorting algorithm to work, if I have any pair of numbers, A and B, and we know that A is less than B, for a sorting algorithm to work, we want to ensure ourselves that A comes before B in the final sorted array, right? This is a criteria for a sorting algorithm to work. Okay, so I think for a quick example, let's just look at the numbers 100 and 200 for A and B. What we will notice here is that since the first digit of A is less than the first digit of B, right? Since 100 at this digit is less than the first digit of B, right? What we know is that since LSD sort, its final pass, right? When we look at this final pass, it sorts on this first digit. We know that when I sort 100 and 200, in that final pass, we'll put 100 before 200 because 1 is less than 2, right? Okay, so we know in the case that when the first digit of A is less than the first digit of B, LSD sort just destroys that situation, right? It does really well. Well, the natural question to ask here is that we know LSD sort, based on this example, will work if the first digit of A is less than the first digit of B, right? But is it always the case that A will always be put before B if A and B share some of the first few digits in common? Okay, so say A is, I don't know, 1, 2, 0, 0, and B is 1, 2, 1, 0. Okay, in this case, we're going to notice that they both share the first two digits in common. Well, let's find the first digit that A and B differ on. Okay, so notice that A and B first differ at this spot. And let me quickly show you guys that spot visually. Give me a second. Okay, so we notice that if I'm looking at A and B starting from the most significant digit to the right, the first digit that A and B differ on is this digit right here. So when I'm running LSD sort and I'm sorting all of my numbers on this digit, what's going to happen is that A will be before B, right? So just recapping that, when we sort all the numbers on that digit is this one that I highlighted, notice that A will be before B. Okay, let me just move this up. Okay, now this is the very, very important part of this algorithm. At this point, we know that A is going to be before B, right? After we sort on this digit. And now, since every other pass after this point is stable, we know that A will remain before B, right? So just kind of putting that here in words, since every later pass is stable, A will remain before B, right? What that's saying is when I'm sorting on the twos, A and B will preserve their ordering because it's stable. Then when I sort on this one, A and B preserve the ordering because it's stable, right? And then what we'll notice is that A must be before B in the final answer. And what we can say is that whenever we have any pair of numbers, A or B, LSD sort will ensure us that A comes before B in the final sorted array. So we know that LSD sort actually works. Okay, so now that we've kind of understood how LSD sort works, the question that arises is, what's an efficient way to sort all of the numbers on one digit, right? When we were looking at this step right here, how in the world did we actually sort all of these numbers on this last digit, right? I never really walked into that yet. So there should be some efficient way of achieving this operation, right? Like if sorting all of the numbers on one digit took the same amount of time as like quicksort, might as well just run quicksort once instead of running it the number of digits times, right? So there indeed is a really efficient way of sorting all of these numbers on one digit, and that way leverages the fact that each digit is in a finite range. Okay? So that's the main intuition here. Since each digit is in a finite range, let's leverage that. And the algorithm that leverages that is called counting sort. So a very quick recap of what counting sort does is this is just doing the first pass of the sorting algorithm of LSD sort in the example before. So let's say that I want to sort all of these numbers on this last digit here. Okay, so what's going to happen is we're going to basically use an array and try to put each number in the spot in the array corresponding to that digit. Right, that's kind of like the intuition for what counting sort does. So to achieve that, we're going to break it up into 3 steps. So the first step here is we're going to count the number of items at each digit. Okay, so when we look at how many numbers have digit 0, we see 2 of them do. So we'll put a 2 here. How many numbers have digit 1? 1 of them. How many numbers have a digit 2? 1. And then we see that there's a 5 and a 9 here. Okay. So the idea here is we need to know how many numbers of each digit there are, right? So that's the first step. The second step is now that I know that there's 2 numbers whose digit is 0, what we can say is that the first of these numbers whose digit is 0 will go at index 0. Okay. Now, this is like the next thing, which I think is a little tricky at first, is we know the number of numbers whose digit is 1 at the spot we are comparing is 1, right? We have 1 of them. So what we're going to do in this case is we're going to say that since there's 2 numbers whose digit we're comparing is 0, we know the first number in our final sorted array whose digit is 1 will appear at index 2. Okay, so the reason for that is we know that in the final sorted array, we're going to have 950 and 120 at the top, right? Just because the zeros make them come first. Then what we're going to know is that when I take the number 121 and I want to put it somewhere in this array, it'll go right here. The reason for that is because the only people that are smaller than 121 are these 2 numbers whose last digit is 0, right? Okay, so what this starting points array is telling us is that the index, this is the index, where we want to put 121 is index 2. Okay, I forgot to label these. And what we're going to see is that we can kind of continue this pattern here. Let me erase these because we haven't finalized them yet. Okay, so now when I look at all the numbers whose last digit is 2, we see that they will go at index 3, right? Because there's 3 numbers before them in the array, okay? Then when we look at the number whose last digit is 5, we see that it's going to go at index, how many? It's going to go at index 4 because there's 4 numbers that are smaller than it, right? If I look at this person, we know that all of these people will go before it. And then finally, this one will be 5. Okay, so the last idea here is now we know where the first number of each of these groups is going to go. We can just put them in the final array. Okay, so I'll take the number 121. We'll see that we want to put it at index 2, and we'll put it there. Okay, So we'll put it at index 2. And the important idea here is that if there are more numbers whose last digit is 1, we want to increment this counter. Because the next time I put a number whose last digit is 1, we want to put it at index 3. Okay? Then what we'll see is we'll go to 452. We will go here and say, let's put him at index 3. So we put 452 at index 3. Okay? Then what we'll do is we'll look at 950. Right? We'll look at 950. Then we'll see that when I go to this spot, it's index 0. So I put 950 at index 0. And then I also have to increase this counter. I forgot to do that last time. Okay, then I see 120. I go to this spot. I see 120 should go at index 1. So we put 120 at index 1. All right. And then we're almost done. We just have to put in 950 and 789. So, oh, not kidding. Just kidding. 435 and 789. So we'll put those in. I'm a little lazy, so we'll skip some of the steps. Okay, so that's the idea of how counting sort works. Well, the last two things I want to go over before we dive into the understanding question is what is the runtime of counting sort and what is the runtime of LSD sort, right? So when I'm looking at counting sort, we kind of have like two factors at play here, okay? This first factor I'm going to say is R, where R is equal to the range of values the digit can take, right? So in this case, R will be 10 because there's 10 values that a digit can take, right? So the second thing we can classify, or that will help us classify the runtime, is this, which I will say is n, and n is what we've seen before in the past. It's how many items we are sorting, okay? So it turns out that the runtime of counting sort comes out to R plus n. Okay, so the quick justification for why this is the case is that when we're trying to create this starting points array, we have to look at each index in the counting array, right? So we have to go here, 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 and so on. So we have to look at the entirety of this array, and this array is of size r. So that's where the r comes from, okay? And where does the n come from? Well, we have to look at each number at least once, so the n comes there. Okay, so that's the quick justification for the runtime. So now when I look at the runtime of LSD, we see that all we're really doing is, if I define W as the width of the numbers, we see that we just run counting sort W times. And if counting sort takes us R plus N time, we see the runtime of LSD is going to be W times R plus N. Okay? So that's the runtime of LSD sort. So yeah, that was a little longer than I expected, but I think this understanding question is rather fun. So I definitely recommend sticking around for this. All right, so this question states is, suppose that we have a set of 4 numbers. Each number is 3 digits, and each number is a binary number. A binary number takes on values either 1 or 0, okay? So we want to find a set such that when I run LSD sort on the initial array, the passes go in this ordering, where A starts here, goes to this index in pass 1, goes here in pass 2, and then finishes it off here. Okay? So we basically want to find these numbers A, B, C, D such that this is the case. So now please pause the video. Do give this problem a try. I think it's rather fun, and it's a good test of like your understanding of LSD sort. It is on the harder side, so keep that in mind. All right, pause the video. Okay, so let's go over it now. So this problem I think is really fun because it leverages the fact that counting sort or whatever subroutine we use is stable, right? So let's kind of go like this. So we're trying to figure out what A, B, and C, and D should be, right? That's what we really want here. So my idea here is let's kind of create A, B, C, and D digit by digit, right? When I'm looking at this first pass only involves this digit in A, right? So what we can say here is that after executing this pass, we need D to go to the front, and we need A, B, and C all to preserve the same ordering, okay? So in order to achieve that, what we can do is I can say that if I'm looking at A, B, C, and D, the last digit in D should propagate D to the first spot. So it must be smaller than everybody in A, B, and C. So this must be a 0 here, and then these all must be 1s, right? Because the ordering of A, B, and C relative to each other stays the same, but then D jumps to the first spot, okay? So now what's going to happen is we will have D, A, B, and C is the ordering, right? And then what we'll see is that we kind of repeat the same pattern, where the ordering of D, A, and B stays the same, right? But then C jumps to the first spot, okay? So what we will notice in that case is that if I'm looking at D, A, and B, they should all have a 1 here, and C should have a 0 here, right? So that C jumps to this first spot, and the ordering of D, A, and B relative to each other stays the same. Okay, so looking at this final pass, we'll see again that it's the case that C, D, and A kind of jump here, and then B goes to this top level. So if we're looking at all of the digits of C, D, A, and B, we'll see that these should be 1s, and this should be a 0. So kind of putting that together, we'll see that our solution is A should be 1, 1, 1, right? 1, 1, 1. B should be 1, 1, 0, or 1, 1, 0 in reverse order. C should be in reverse order 1, 0, 0. Oh, just kidding. 1, 0, 1. And then D should be 1, 1, 0. Okay. So that is all for this video walkthrough. I hope you guys found it helpful, and I hope you all found this problem a little fun. So yeah, have a good rest of the day.